Hello? Hello? Hello, hello, hello?
I'll keep talking.
Hello, hello, hello? Okay, awesome. All right. All right, so welcome to our talk. It's Papers, Please, Scrutinizing AI Model Creation. So I'm hoping everybody in the room has heard of the game Papers, Please. So it's kind of a play on that. So it's like, you know, we want to be scrutinizing how was the AI model created? You know, is it signed properly? Did it have the right documents? And is it allowed to move into, you know, can we use it and so forth? Right? So quick introduction. I'm one of the co-founders of a supply chain security company called Kusari. I'm also an open source maintainer on the open source project GUAC, which is a graph for understanding artifact composition. And we'll talk about that coming up. Another one is Fresca, and then in toto attestations, which actually the SLSA attestations and other things are built on, and we'll talk about more. And then in toto Golang.
Hello, I am Mihai Marusak, the same way as Taylor Swift, it's Mihai. I am from Google Open Source Security Team, also known as Ghost. And I co-chair the OpenSSF AI working group for AI and ML and security, and also member of the Haskell security team. And for open source, I started with TensorFlow security. I started the team, and then I started maintaining TensorFlow, and also maintainer for GUAC, model transparency for AI supply chain security, and Hindent is a Haskell indenter. And now let's go into the talk. So let me first put on an attacker hat. And suppose there are these users that I want to impact, to inject malware to them or to cause harm to them. And I want to do this via AI. So I'm going to build two models. One of them is going to be an evil model that will have malware, and the other one is a GPT 4chan, it's a LLM trained on 4chan. And I want these users to use these models. Of course, I cannot just send the models to the user directly. I have to upload the models to a model hub, and I have to give a description to the model in the model card. And now the users would likely download the models and use them. Well, this doesn't really work that well, because users are going to see that the first model is called evil model, and they're going to say, no, I'm not going to download that. And the second one, again, from the name, they're not going to download it. But that's something that I can easily fix. I can just change the name to the model, and now users will not be able to know what is the problem. So that's the main thing that we're trying to solve, is trying to tie the model to how it was built in a way that is tamper-proof and stored in attestations and so on. And this is not theoretical questions. Just a few weeks ago, a ByteDance intern got caught sabotaging another intern by sabotaging the model pipeline and ingesting malware and reducing the way a model gets trained just to get ahead of another one. So let's think how AI is being developed. Initially, you start with some data sets. And if you train from the internet, you just don't build the model directly from the dataset. You perform some iterations on the dataset to clean them up. You might have missing data that you fill in. You might run some rounds on scheduling the data, on massaging the data to fit certain forms and so on. Once you have the dataset, the next step is to select a model framework like TensorFlow, PyTorch, and so on. Decide on the model architecture, and combine everything together to train the model. And now that you have your model trained, you put somewhere in storage, and you are waiting for this model to be used. Well, actually, there are two steps. One part is for large models, you don't train everything in just one single step. You train one step, put it in storage, get another data set, train further, and so on to fine-tuning. So you have this iteration going back into the training process via pre-trained model. And at some point, you get this model and say, now I want to put the model into an application. You elevate it to a production model. You do a release, and then you embed it into the application. So this is kind of how you build AI models in general. This is like a 10,000 feet view of building AI. And of course, at every step in the process, there are supply chain risks. So you could have, during the data transformations, someone maliciously or by accident could ingest data poisoning. And now all the models that are going to be trained on that data are going to misbehave. Or from the model source, the source repository itself could be tampered with, and you're hoping to train one model, but because the source has been tampered with, you're actually training something else, a model that might have malware ingested into it. Or even let's go to storage. You put your model in storage, but then people that have write access to the storage might overwrite your model with something else, or might just modify the weights a little, fine-tune the model to mispredict under some conditions. So we want to protect all of the supply chain. And the first step is each time we release an artifact, we sign it. And each time we use the artifact, we verify it. We can use Sigstore for this. There was a talk yesterday about Sigstore. This is very easy. But we can go one level further because signing only tells you that the bits of the artifact are expected to match this hash, and that's all. But it still doesn't tell you who built the model and what got into the model. So that's the second part that we want to do. And for that, we can go to the next step from traditional supply chain security. We can use SLSA. SLSA attestations can record information about all the inputs that come into the build process, information about the build process itself, and information about the output. And we can look at some SLSA statement.
Yeah, so the SLSA statement kind of starts off like, if you've seen traditional SLSA statements, they're usually describing software artifacts, right? So how was it built? Where did it come from? What artifacts, what are the materials that kind of went into it? So we can apply the same kind of methodology for an AI model also. So you can see here, for this PyTorch model, you have the specific hash, which describes the actual object itself. It's the subject of the SLSA attestation. From there, we see if we query the builder, you can see where exactly it was built from, and then we can see the materials. But materials currently is only listing the source repo, where exactly it came from. Because SLSA was originally designed to capture software dependencies, how the software actually is built, and not for an AI use case. We can actually, it's not fully complete, right? We're missing information about this. So that's where, we have the subject is being handled properly via the hash and so forth. But in order to complete the actual SLSA attestation, we need to include the data sets that kind of went into it. And then other, iterations we made on the data sets, how was the model actually trained, and then finally what kind of framework all went into it. So we need a complete understanding of how exactly it was built, so you can put that into the SLSA attestation, right? So this information is currently missing. Currently we're using GitHub Actions, but we want to in the future, have this ability available for other ML trainers and so forth, as well as for the developer, right? So if they're working at Jupyter or Collab, we want this in the hands of developers so that they can easily create these SLSA attestations as they're actually working. And it's not something that they have to do extra, right? It's as they're kind of working through their workflow, this information is getting collected, placed into an SLSA attestation so that it can be consumed. So we have three different things here, right? So we have the SLSA, which is focused on how was it actually built. Model cars, right? This focuses more on the ML, like the data sets, licenses, and so forth. So what we want to do is take all this information, combine it all together in the SLSA attestation, but from there we can actually create an AI bomb or whatever else kind of we want to, right? So an AI bomb will contain the actual artifact, the dependency tree, and so forth. So we want to take all this information, but a starting point is we have to create a SLSA attestation that is complete.
So going back to the diagram, to the supply chain diagram that we have seen before, we can see that we have these two loops from dataset to dataset, and then from model, you train the model, you put it into the hub, and then you iterate again on it, and so on. And thinking a little bit deeper into this gives us the idea of dependencies. Each time you build a model, it has several dependencies. Some other models it has been trained on, some dataset it has been trained on, even the training framework, even the ML framework, TensorFlow, PyTorch, and so on. So thinking of dependencies, let's first think on how the traditional supply chain world works with dependencies. So let's look, for example, at the dependency tree for TensorFlow. When you do pip install TensorFlow, all of these packages are going to be installed into your system. And when you look at the graph, we see that TensorFlow has a bunch of dependencies as the first layer, a bunch of direct dependencies. And then each one of them has a few of them. In general, for traditional supply chains, for the traditional software environment, the dependency tree is wide, so you have a lot of dependencies at the first few levels, but also narrow. You don't go beyond 5 to 6 levels. Of course, this is in the majority of the cases. There could be pathological cases where you have thousands of dependencies and so on. Now, if you look at ML, the process looks a little bit different. This time, the tree is shallower because each model has been trained from one data set and one pre-trained model. So you only have just a few dependencies, but also the tree is much deeper. You have many more levels into the tree. So here we have some example. At the bottom down there with yellow is a model that is trained from one data set. That's the case that usually happens for very small models. In general, it's more like experimentation. You want to see if this model architecture is able to learn information from the data, but that model will not get into production because it's not trained on enough data. What usually gets into production is what's shown on the slide at the top. You start with one data set, you maybe perform some operations on that and you train a model, or once you have a model, you might fine-tune it with data from another data set, and you keep iterating on these steps, and then at some point, you take this model, the final model, and then you convert it to some format that the application can use. So for example, you can quantize the model if you want to deploy it in mobile applications. Or if you train a very big language model, like with 8 billion parameters, but you want to use only 2 billion for performance reasons, you can do model distillation to reduce the size of the model. And other operations like this. So that's how the supply chain, the dependency tree for ML looks like. You start with one model and you have just a few dependencies and multiple iterations going back. And now if we have SLSA attestation for every step into this process, SLSA attestations that are complete, so that record both the input and the output, we can now analyze the entire graph with both humans can read the attestations, but also we can use tooling. And that's what we're going to go into this for the remaining of the talk. So we have worked to extend the SLSA. Instead of just providing the final output and the repository, we also worked to also record the data sets and the models that go into producing the model. And then we used some tooling that we're going to talk about that to analyze this entire graph.
All right, so just to recap here, right? So we talked about SIG-store. So at the bottom here, at the right, you can see that SIG-store. So that's where we're doing signatures. It's providing us with strong identities. The next level above that, which is in blue, is the software or the attestations. That's where SLSA lives, right? This is giving us the combined information about how it was actually built. And then the next piece is GUAC, which is the graph for understanding artifact composition. And I'll go into it a little bit deeper in the next slide. But basically, right, you have all this SLSA attestation, all this metadata that's laying around. How do we take this information and make it usable for us? Like I want to automate policies around it. I want to gain some more insights. Can I use this information? Like, right, it's going to be separate documents. Can I take all this information, throw it all together, and then can I use it for policy? So that's where we're kind of getting to. So GUAC, so this is an open source project that both Mihai and I are maintainers on. So it started off, we wanted to be able to ingest, software metadata in general. So we wanted to make this very flexible. So GUAC is very pluggable. So right, it currently takes in, SBOMs, it takes, software bill of materials. It takes in scorecard information, OpenSSF. It takes in toto attestations, which is like SLSA and so forth, and vulnerability and all that kind of stuff. It takes all this information, puts it into a graph database, and then from there, you can use the API in order to query all the information together, right? So it's going to decompose all these artifacts and decompose all these documents, and then put them into a graph database that they're all interconnected. All the relationships are defined, and then you can use that information to make policy decisions or whatever else. And one of the things we'll get to is, like, for example, let's say that the data poisoning example happened, right? Let's say one of the data sets was compromised. Then how do you know where did you use that data set? Can you find out quickly instead of, it's a guessing game because you might not know exactly what data set kind of went into the model to get it trained. But if we're combining it together, having SLSA, SIG-store, and GUAC, you can query for that specific data set and find exactly which model was actually is actually being used by it. So let's kind of jump into the demo here. So I quickly got, so GUAC is up and running. So on the bottom, basically, it's just up running. So what I'll do here is I'm going to ingest. Like Mihai was saying, we went ahead and created SLSA attestations for all these models. So we are going.
Bigger.
That's too small still?
Yeah. Okay.
Good, okay. All right, so what's gonna happen is I am going to ingest all these SLSA attestations that we already generated, and we'll talk about some of the attestations, the materials and so forth a little bit later on. But basically, it's going in, it's decomposing all the information, like I said, and it's gonna put all this information into a graph database that's behind the scenes that's running. At the same time, we are also verifying. So here you can see verify signature against transparency log. So we're using SIG-store. So all the data sets, all the SLSA attestations are all signed. So as they're coming in, we know haven't been tampered with, and what information that we collected was accurate from the source, basically, right? So each of these documents were signed, and then as they were ingested into GUAC, we're verifying that they were the documents. They're saying what they are, kind of thing, and haven't been tampered with. So the first example we're going to run is the PyTorch model that Mihai kind of talked about. So I want to hear it real quick. So basically, I'm just querying at the top level subject artifact, and I want to see what exactly, what information is there and what materials were kind of composed by it.
So this is the scenario where you have a model that has been trained from one single data set. We use the hash of the model, and we want to find out what are the files, what are the images from the data set that the model has been trained on. And this is what we see here in this table.
Yeah, so this table is here is the actual, this file, that's the salt statistician network, that's where it came from, and it's describing this SHA-256 hash, and you can see all the materials that are part of it. This includes, all the different data sets. It could be the framework or model, whatever else it is, right? Everything that's been trained on. And if we kind of search this, each one of these will have their own salt statistician associated with it. So you can see this material has its own salt statistician down here, which is part of this data set salt statistician, and you can see the material that it was trained on. So it's going to be recursive, so you can go all the way down the down the tree, kind of see and understand exactly what kind of composed, what's composed within each layer, and then as you go down, you can understand, okay, what material is there, and this is how you understand where everything kind of came from, right? Anything else you want to add here? Awesome. Okay.
Okay, so now let's run the second demo where we are looking at the model in production, and we want to see the entire graph of dependencies from the first data set to any data set that got fine-tuned, any model, any fine-tuned model, and so on until the end of the model.
And I forgot to show this off.
Oh,
and so we do have our visualizer that we have running here, and it zoomed out, which is not good. So zoom in a little bit.
Yeah, so this was the PyTorch model. We can see this node, the pink circle here. This is the PyTorch model, and as dependencies, we see all of these salsa nodes here. These are the data sets, the images from the data set that have been used to train the model.
And you can see they're all linked to this salsa generator. That's where they were built from. So, and this is this particular hash, and they all are linked together with the salt statistician. So this is behind the scenes. You can see the graph database kind of taking all this information and correlating all this information together. And it's kind of hard to visualize here, right? Because there's a lot of information. So we're still trying to work on this. We're trying to make it so that it's much easier. It shows you the relevant information, and at the same time, it gives you the information. Doesn't crowd it all together. So this is still a work in progress. That's why it's a little bit like that. But yeah. All right. So this is the other model, right? The production one.
Yeah. So you can see that this is the CFAR 100 fine-tuned model.
Yeah.
And that's where it comes from. And the materials again contains every dependency that got into that model, and you can search from that dependency. You can see every dependency that got into that, and so on. But we can also display this into the visualizer. Same as before.
Yeah, and then you can see again, each one of these data sets may contain other materials, and so on and so forth, right? So it's all being recursive, and you can see it's pretty large in here. So again, I can take this visualizer, and we can view it here. And I apologize that it keeps zooming out. There we go. All right. Yeah, so here's the actual shot we kind of started with, and then you can see all the different, again, you can see all the different, the data sets and all the other kind of things that are associated with it.
Okay, so now let's do the other scenario. Now let's say that we discover that some data set has been poisoned, or maybe the images from that data set become illegal to use. So we are going to use GUAC to detect which models we need to retrain, which models are impacted. And we are going, for example, to say that based on regulation, this set of images cannot be used anymore for training. So we are going to certify that set as bad. We mark that into GUAC, and then we can query the GUAC, the graph database, to determine what are the models that are impacted.
Right. So what I went ahead and did here is I marked that specific data set as bad, and then now I'm going to do a query on it. So once it returns, it's going to give me, so here is the certified bad that I created at the bottom. And from there, it returns me a visualizer. And again, we can output this in the CLI in another format. So again, it's still a work in progress in terms of how do we display this information. So it's a lot easier for the users as well as anyone that's kind of looking at this to understand. So let me zoom back in again. right? So here is my certified bad node here. You can see that I've certified this particular data set as bad. And then I want to see, okay, where is it being used? So here's a direct SLSA attestation that's attached to it. And then you can see that this is the particular model that has actually been that has been trained on, right, on that data set. So that's the one that's kind of affected. And then you see there's another SLSA attestation here. And you can see because there could be recursive nature of the model training. There's a lot of different places where it can be used and so forth. So this gives you an understanding of like if the data set was poisoned, how do you quickly determine which models are affected, and then what do you need to go remediate, right? It's kind of the same example. If you heard of the log4j example continuously, right? So it's like, how do I know where log4j is in my environment? If I can map it out properly, then I can just query for it, and I can find, yep, here are my different softwares that are affected in production or whatever else. The same kind of concept here. It's like, how do I know if this data set is affected, and then which models are, if I'm using it in production or whatever else, how do I know if they're affected?
So the idea here is you have your model put in storage, and now somebody decides, I wanted to take this model and put into some application. And as soon as the model gets taken from storage and you compile the application, if you integrate with GUAC, GUAC will fail the build and will tell you, you cannot use this model because transitively it has been trained on these images that are no longer supposed to be used. And the hash that we have passed for the image doesn't have to be the hash of the entire data set, could be the hash of a subset of the data set, as long as GUAC knows about that hash. So in our case, it has been just a subset of the images. It's not all of them.
Yeah. Yes, that was the important point of putting this into a graph database so that you can use the graph nature of everything to query the information as you need, and then apply policies on top of it, like Mihai said. Okay, so let me go back to this. Is there anything I don't? Right. Awesome. Yeah. So thanks for listening. This is we're using SLSA, Sigstore, GUAC all together so that we can give a complete understanding of how the model was built and then create policies and so forth around it. And I did want to give a quick shout out. We're having a happy hour tomorrow, so if you're interested in talking more about this, be sure to join us. Mihai and I will both be there. So thank you. Any questions?
Yeah, questions.
Hi, so how would this work if you have like a continuously growing data set? So like imagine you're doing like a web crawl, so you're continuously getting new data or something. How would you version that in order to like have the attestations about that?
So you can build Merkle trees on the data set. You'll have, this is the data set that has been before. I ingest more data from the internet and now I build a new data set. The first data set would come as the input for one SLSA statement. And the full data set, that is the Merkle tree of the previous hash plus the hash of what I got now from the internet, will be the output. And that's how you can get the chain. Like this is the first part of the data set, then once I get more stuff from the internet, I'll have another hash, and once I get more stuff from the internet, I have another hash, and so on.
I see.
Yeah, so it's kind of mixing, like similar to Git. Each time you put a new commit, you still have a reference to the previous commit.
Okay, got it.
Tim? Any more questions? Yeah, back here.
Do I understand correctly that the current state of things, there has to be a person who just goes in and says, oh, this model, this data set, this piece is bad, right? So there's no like current scanning, there has to be someone coming in and actually marking it. And I guess follow up to that is like, you talked about as long as the hash is in the database, so there's a possibility that some data sets in the model could not be in the database, right?
Okay, so for the first part, right now we just mark the data set ourselves to be dangerous, but GUAC also supports the concept of vulnerability scans. So for traditional software, we are connecting to ASV and getting the vulnerability data from there, and then you can query based on vulnerabilities. There are some startups that are trying to look for vulnerabilities in ML metadata, in ML models, ML datasets, and so on. We can integrate with those two and then use the same approach. Now, for the second part about, let's say, image 1 and image 20 from the dataset are the ones that I shouldn't use, but my hashes are covering the entire set from image 1 to image 100. I can still find that hash, and that will be the hash that I mark as bad in GUAC. And I'll have a larger chunk of the data set that cannot be used anymore, but at least I'll still be able to know which are the models that definitely don't need to be used in production anymore.
Yeah, so I think in the future we can automate once like the AI vulnerability and all those kind of become more prevalent, similar to software vulnerabilities. We can just come in automatically, either create that node for you automatically based on online feeds and whatever else. So it doesn't have to be manual, but like at this point it is manual.
Questions still? Going once, going twice. All right, thank you very much.
Thank you.
Thank you.